Okay, so thanks a lot for coming back, guys. Now we've done NVs 101, so we can do NVs 202 and talk about some techniques or various things that one can do with these color centers, with these NVs, with these solid state spins. And of course, what I'll tell you here is is highly biased by things that I know or think I know. and if and of course, there are many other things that you guys probably are working on or are interested in, and there's a lot of interesting things in this context. So, what I would like to try to focus on is some ideas related to quantum information and control. Spin degrees of freedom. So, talk a little bit about dynamical decoupling and noise spectroscopy and hyperpolarization, and also many body systems. And then a little bit about sensing and some techniques that are associated with sensing and how to get it to be maybe more efficient. So let's start. And this you've already seen. So we know about the noise and how Hahn echo or dynamical decoupling can help us get a better coherence time, what we call T2 in the NMR jargon, compared to the T2 star of the Ramsey experiment. And this is just an example of these measurements that I mentioned before, where these are the actual measurements where you measure the signal, it's the fluorescent signal, right? But it's the spin fidelity as a function of time, and the different colors are different numbers of pulses. You can see that the signal is decaying more and more slowly as the different colors are increased numbers of pulses. So this is the standard result of how you can increase T2. The black line here is an actual T1 measurement. It tells you what the limit is, okay? Because T1 is, again, phonon dominated. It's this relaxation process that our pulses are not efficient against, and that's why we can never reach it. Now, we were talking about these types of relaxation processes. We talked about the Ramsey envelope, we talked about echo and CPMG and whatever, and T1. And we were always saying you have this exponential relaxation. I even asked you what would be the best measurement strategy? Which time points would you choose to measure to get the best estimate of your relaxation, T2, T1, whatever T2 star. But the relaxation process, as I'm sure some of you know, doesn't follow an exponential curve. It actually looks like a stretched exponent most of the time. So I leave you with a question: what is the best measurement strategy for a stretched exponent? Nobody knows, actually. So if you come up with an answer, it's a nice paper. So why are our relaxation curves not exponential? Why are they stretched with some power alpha? Okay, so Arnie is waving at the mic. Nobody's thinking. Someone there wants to answer, but he knows everything, so it's not fair. So since I don't have an exercise for you to, like an exercise slot, I'll just give you an exercise. So what is the relation between T2 star or T2 and T1? And some of you who are familiar with NMR textbooks might have seen a relation that says that T2 is twice T1. Has anybody seen that? Somewhere? Someone. Anyway, why is that true? Is it true? Okay, so I would, since I don't want to keep you for too long, I'll kind of leave you with these questions, right? But all the answers are in this very, very nice paper that I recommend that you read if you haven't already. Of course, it appears in many different places as well, but this nice review by Rogério de Sousa I like it a lot. It's very clear. So in principle, T2 equals twice T1 if the only process that you're encountering is relaxation. There's no dephasing. If there is dephasing, it will be smaller. And if it's not a two-level system, it would be something else. And all of these relaxations come from it's not like, it's not given. It comes from the fact that we have coupling to something in the environment. I don't know, C13 nuclear spins, other electronic spins, whatever crap. It comes from some environment. And the characteristics of the environment will tell you what the effective relaxation is. So, for example, if you have spin baths, excuse me, they usually can be approximated by a Lorentzian type noise spectrum. So the content of the noise in frequency space follows usually some Lorentzian function. This Lorentzian, if I'm trying to be fast, but I'm also trying to be useful. So if you're not familiar with this, I recommend that you read some of the background in this because it's very, very nice physics, dating back to some older papers by Clowder and Anderson from '62, and then later on. But read the old papers, by the way. This is kind of a little tip. The old papers are usually the ones that people remember are very good, very, very good. So I recommend it. So you can approximate it by this Lorentzian, and you can think about the physics of why this looks like a Lorentzian spectrum. It has two parameters, delta and tau c. Delta is an energy scale, tau c is a time scale. So think about your NV, for example, with a bath of other spins around it. What would be the energy scale delta? It's the energy scale of the effective coupling between your quantum system, the spin that you're measuring, and this bath, and these other spins in the bath. Of course, it's somehow an effective coupling because they're all distributed around, so it's some kind of average quantity. So this is one parameter of the Lorentzian. What the other parameter is time, is tau c. What do you imagine this tau c would represent physically for this spin bath? You have a bunch of spins coupled to your quantum system. Delta is the effective strength of the coupling. What is the other parameter that describes the bath? Has nothing to do with the NV itself, with the quantum system. It's only a property of the bath. It's a time scale. So it's how fast this bath changes. Okay, the spins in the bath, they can talk between themselves, right? They have some interaction between themselves. So they can, flip-flop or do stuff. So tau c is the memory time of the bath. For example, if this spin bath around your NV is mostly nuclear spins, tau c would be long, short, very long, because they're nuclear spins, their coupling is weak. If it's electronic spins, it would be short, because they couple more strongly, okay? So these are the two parameters that can very well approximate the coupling, the noise from a spin bath. And you can already see that, for example, if the spin bath is changing quickly, tau c is very short. If it's changing slowly, by the way, if it's changing so slowly that tau c is almost infinite, this is a static bath. It's just an homogeneous broadening. It doesn't change. So Hahn echo would be super efficient, right? It would kill everything, all the noise, right? So the decoherence, if you calculate what would be the decoherence in a Ramsey experiment as a function of time, it's this. It's not an exponent. It's something disgusting. Okay? And that's why when you measure this, you don't really see an exponent. But I leave you with the question, this is an expression, but what happens if you take the limit of tau c going to 0, which is, again, a bath with a very short memory time? This is what we usually call Markovian. It has no memory. Tau c goes to 0, it has no memory, it's changing super fast. You can plug that in and find out what the decoherence would look like. Any guesses? You all know the answer, I'm sure. Markovian bath, it changes extremely fast. No memory. What would the relaxation look like? This terrible expression, what would it sort of asymptotically go to? I have all day. No, actually, I don't. it's going to look like an exponent, a real exponent. This is the only time where the relaxation looks like a regular exponent. So all the, nuclear physics that you study about, all kinds of nuclear decays and everything, where you always see exponential decay, the underlying assumption is that it's tau c goes to 0. This is Fermi golden rule, okay? So in this limit, it goes to an exponent. In this limit, it does not. And what would it tend to when tau c goes to infinity is homework. And the answer is here. Okay? And the fact that we see this, we see the relaxation time increase as we increase the number of pulses. What does it tell you about tau c? That it's not 0. It's not very short. Because if the bath that's causing this relaxation has a very short correlation time, tau c is a correlation time, it's Markovian, I could put in as many pulses as I want, and nothing will change. They will all look the same. And this is the story with T1, usually. Okay? So the fact that we see this change in the coherence time, the effective coherence time, suggests that the bath is not Markovian. This cannot be an exponent with alpha equals 1. It has to be some effectively stretched exponent, and that's what we see. Actually, how efficiently can we extend T2 with the number of pulses depends on the effective alpha. You can also see that from here or from here. Okay, and we've seen this already that it works. So I want to now flip this around a little bit, right? I told you that we have noise, whatever bath it is, it causes relaxation, and we can measure our coherence time, given that bath or, with any types of pulses that we apply. And usually we apply these kind of sequences of pi pulses, what we call CPMG. But you can sort of flip this around and say, I don't necessarily want to extend my coherence right now. I don't want to get the best T2, but I want to really study what is my noise bath? What is it made from? What are its characteristics? And one question that you can ask, this is an actual spectrum that we've measured with an NV, and it actually has this kind of Lorentzian shape. So the simple question that you can ask, what are the parameters of this Lorentzian? I mentioned before delta and tau c. Let's measure them. And the way we do this is we can actually think about this pulse sequence as kind of a lock-in amplifier, right? Because we're actually modulating our system periodically with these pi pulses. And if you think about this temporal modulation, temporal periodic modulation, in frequency space, it's like a frequency filter, right? So it's as if you're really modulating your system, and you become sensitive. The decoherence that you're measuring under this modulation is the frequency component of the noise at that, effective frequency, which is approximately pi over the time between the pulses. So if I now can, I control these pulses, I make them. So I can change the time between pulses, I can change the number of pulses, so I can move this frequency window around and basically measure this point, and this point, and this point, and this point, and extract the power spectrum of my noise. So this is a nice technique called noise spectroscopy that we've used, but also is completely general. And there are many examples of how this has been used. There's examples in trapped ions and in superconducting circuits and in many, many other systems. So it's a very nice and general technique to use your qubit, your quantum system, as a sensor of the noise to understand what the environment is. Now, a more general way of looking at this is to say that the decoherence looks like some functional e to the minus chi of t. And actually, you can show that under simplifying assumptions, this chi t is basically an overlap integral between whatever pulses you apply, whatever filter function in frequency space we apply, this is this FF, and the actual noise spectrum that you have. So this is what determines the relaxation that we measure. So ideally, what would you choose for your filter function? Because you want to measure S of omega. I want to know what the noise spectrum is. So what would I choose for this FF, ideally? Thank you. A delta function in frequency. So if I can create a filter function that's a delta function at frequency omega 1, I immediately get S at omega 1. And then I change it to omega 2 and so on and so on. So that would be ideal. We don't know how to do that, of course, because creating an actual delta function is hard. So we tried to do, to approximate it. So as I told you before, our initial approach was to just use the regular CPMG, the sequence of pulses. This is what this looks like in time, because we're just modulating up and down, right? And if you look at the Fourier transform, the filter function in frequency space, it's kind of like a sink. So it's a little bit like a delta function, but with these little wiggles. But also it has higher orders, right? Because this is not like a nice sine. It's basically kind of like a square wave, right? So it's an okay approach for doing this spectral decomposition, but it's not so great. And now you can already suggest to me the better way to do this. Yes? Suggest to me. Come on, we want to get a delta function. What would you do to get a delta function?
Use a sine wave?
Of course. The best approximation that we can have for a delta function is to just drive it at one frequency. Of course, it would not be of infinite duration, so we'll always get some crap around it, but that would be the best thing. And actually, there are slightly better ways of doing. I mean, keep in mind, what is a sine wave? It's basically just, Robbie driving, it's just driving it all the time. We know that Robbie driving is not so great because it introduces noise on its own. So there's some modification to this. I don't want to go into the acronyms because people in NMR love acronyms. So there's something called DISCO and GDISCO. It's essentially continuous driving, like Ali suggested, but with some phase modulation that can control the frequency that you're actually probing. The G thing here is to give it a Gaussian envelope to get rid of the oscillations on the side that you'll always have and to kind of smooth them out. But the point being is that you want to make it as close as possible to a single frequency drive so that the filter function is as close as possible to a delta function. Now, I don't want to go into too many details. It's kind of interesting and useful depending on what you want to do. And the bottom line I wanted to show you is that you can actually take the CPMG filter function that I showed you before and improve it with this DISCO thing to get to remove the higher order terms. And also you can use this Gaussian envelope to smooth out all the fluctuations. Look, if you notice, you pay a price. And the price that you pay is sensitivity. The strength of your filter function becomes smaller, so you're not as sensitive. So it depends on what you want to measure. And these are just some results that I wanted to flash, that you can combine these different techniques to do noise spectroscopy that's on one hand maybe more sensitive, but less precise in frequency, versus less sensitive and gives you a sharper feature. And these could be important when you're looking at non-monotonous spectra, for example, and you really want to understand what's going on there with high spectral precision. So there's a lot of games to play in this world, depending on what you want to achieve. And when we were doing this a few years ago, we thought that we know everything. And then, and of course, what I'm telling you in the context of just characterizing your environment is more generally something that people, for example, in quantum computing, do all the time. They want to know what are the noise sources that are affecting their qubits so that maybe they can fix it, or maybe, fight it in a smarter way or whatever. But people in quantum computing, and we looked into this together with Ramuz Dean from our chemistry department. When they're looking into this, they always think about scaling up. if I have, one qubit, one spin, one NV, okay, I can do all kinds of games. But they want to be efficient. They want to be good because they have to do it on many. And sometimes, they have kind of a very difficult control limitations on what they can do. And one of the questions that they've been asking, and Ram was asking before me, was, you want to apply all of these sequences, all of these kind of noise spectroscopy schemes to measure the noise that you have. But as you all know, when we apply all of these controls, they're never perfect. So I want to do like a nice CPMG, or I want to do like a nice kind of oscillating control signal, but I'm doing something a little bit different. So when I'm measuring the relaxation, I'm measuring both the actual noise and the kind of the control errors that I've introduced as well. And separating between these two things is not so easy. So Ram was thinking about, and he calls this, is it here? Unitary errors versus non-unitary errors. So he was thinking about how can we separate these two things so that we can only measure the thing that we're interested in, and not the noise that we're introducing. And the idea he came up with is essentially saying the following. We apply some unitary when we do our noise spectroscopy experiment, but we can apply, it's not perfect, right? We want it to be perfect, but it's not. But we can apply this once or twice or 3 times. We can do, whatever we want. So we can use this periodicity, this repetition of our sequence, to learn something. And what Ram showed, again, I'm not going to go through all the details, but you can read them here. What Ram showed is that if you're measuring your fidelity, let's say this is the fidelity at the end of the sequence, what we usually measure when we do this kind of noise spectroscopy or dynamical decoupling. And you measure it as a function of the number of repetitions, let's say, once or twice or whatever. You can show that if you take a nice, kind of a well-chosen weighted sum of these measurements, of these RKs, the weights are actually well-known. So all of these AKs are well-known. You can actually calculate it from the van der Waals matrix of the dynamics. So if you take a weighted sum, we call this sum sigma n, and the n here is if we do it, if it's 2, we do it twice. If it's 3, we do it 3 times. You take as many as you want. You can show that this sum cancels the contributions of the unitary noise and retains only the actual noise that you're interested in. So you're basically summing these things up in a smart way to get rid of the noise that you're not interested in, the unitary technical noise, and retain only the noise that's actually there. To be honest, this theory is only precise for Markovian noise. For some reason, it also works for non-Markovian noise, which we don't really understand yet. But in principle, that's how it was developed. And to do this experiment, we just did it on a simple NV, measuring, this is a Ramsey experiment, so just measuring Ramsey relaxation. And we wanted to be able to see how we're sensitive to coherent and incoherent noise. So we added coherent noise by adding some microwave drive that shouldn't be there, right? This is like an error, and we can control how strong it is. But we also added kind of this additional laser, which introduces additional relaxation. So if our relaxation normally is like this is a T2 star measurement on one of our NVs. When we turn the laser on, we see something else that's much shorter. Okay? Quick kind of refresher question. This relaxation is long. It's about 20 microseconds for a Ramsey experiment. And it has this weird shape. Why? It's a measurement of a single NV. What can you guess about this NV? About this relaxation? Does this relaxation look exponential? Not really, yeah.
As a non-zero TC, tau C.
A very long tau C, exactly. So this relaxation was measured in a sample that had very low C13 concentration, and very low nitrogen concentration. So it was dominated by a kind of a weak nuclear spin bath. So the relaxation time is long, and the relaxation is very non-exponential. It's actually a stretched exponential with a power that's close to 2. So this is what it looks like. When we turn the laser on, we're actually sort of like inducing relaxation through the optical pumping process. So we chose the intensity of the laser so that it's the dominant relaxation. You can see it's on the scale of a microsecond. It's much faster, and it looks exponential. Okay, so we can play with these things in this sample. And again, just to do this quickly, we now do the experiment, this exact experiment that I just showed you, but we can calculate from periodic time measurements. We can calculate these sums, this sigma 3 in this case, we can calculate sigma 2, sigma 1, sigma 4, whatever, and plot it. These are experiments and simulations, but we can plot it as a function of time, where the different colors are the strength of the microwave drive. I remind you, the microwave drive is this coherent error that we introduce into our experiment, sort of by hand. So as we increase the strength of this drive, we're introducing more coherent errors. So you can see that we're quite insensitive to these coherent errors up to relatively large values. The green is the largest, and up to relatively long times. So taking these C3 sums allows us to get this pretty robust measurement. And I didn't add it here, but we can actually use this approach now to measure, for example, T2 star, right? Some of the standard characterizations that people that we do, but also just a second, also in quantum computing, they want to measure the phasing times and coherence times. This allows you to measure these without being sensitive to any coherent errors that you have in your system. Question?
All right, what's the vertical axis in these plots?
Yeah, so this is actually this sigma 3 value that I mentioned earlier. So we basically measure the fidelities at time 0, 1 repetition, 2 repetitions. In this case, it was sigma 3, so up to 3 repetitions. Take this sum, and these are the values that are plotted. Okay. Other questions? So when I was telling you about this kind of noise spectroscopy approach, it's extremely powerful, but you have to keep in mind that you also are introducing some imperfections from the control that you're applying, and there are ways to kind of take this into account as well. So let me go on to tell you about ensembles a little bit, because what I showed you so far and what we've talked about also in the previous hour was all at kind of like the single spin level. There was always one NV, and if we had many NVs, they didn't care about each other. But sometimes we want to have lots and lots of NVs. Why? First of all, it can boost our sensitivity if we want to measure something interesting. But also the dynamics of a dense ensemble of NVs could be quite interesting. And it could be very interesting where you, at the level where the density of these NVs is so high that they start talking to each other. And then the dynamics of the system become quite non-trivial. So sometimes we want to have a dense ensemble. One of the issues with these dense ensembles is to really be able to talk to them properly, because there's many of them. So one thing that we've done, actually Fedor is not here yet, so I will not mention him at all, but it was done together with him, was to try to use this for sensing. And to be able to do this properly, we've taken a kind of a diamond with a dense ensemble of NVs. And we've developed tools to address it efficiently. We created this modified split ring resonator structure to drive microwaves homogeneously along the sample. When I'm talking about inhomogeneities and addressing this kind of large ensemble, I'm talking about length scales of half a millimeter or so on a side. So not huge, but still trying to address a relatively large ensemble. And we've also developed this kind of optical collection scheme to be able to get light efficiently out of the system. And when you have these tools, it's kind of nice because first of all, you can talk to this large ensemble, but you can talk to it pretty well, and you get a good signal. So I'm always amazed by this measurement because it looks like a simulation. But these measurements, because the SNR is so good, you get these very nice measurements very quickly. Let me just ask you very, very quickly. We've developed this, so this type of resonator structure for driving microwaves is well known. This is called the split ring resonator. And the addition to that we've done in order to create something that would be homogeneous in three axes is to make sort of like a Helmholtz type structure out of two of these, so that we can get homogeneity not only in the plane, but also perpendicular to the plane. So, yeah. Like a Rabi frequency? Or the microwave frequency? Yeah, so that's a very good question, which is actually what I wanted to ask. So, so you can go, it depends on the design of the resonator, of course. You can go to very high frequencies with these. We were, of course, focused around the 2.87 gigahertz of the NV, but you can play around. But I was going to ask, actually, if we build this type of resonator structure, as opposed to, say, the standard antennas that maybe some of you use and we definitely do, what are the the advantage of using a resonator like this is usually that you can enhance the power, right? Get stronger microwaves. What would be the downside? Why heating?
High power, you get a lot of heat.
Well, but let's say, for example, that the fact that we have this kind of relatively okay resonator structure means that I can use the same microwave power as I use for your regular antenna. Heating would be similar. Heating could always be an issue, I agree. But let's say this is not different than another antenna structure. I'm sorry? Excellent. Why? Perfect. So the price that we pay for this, and the price that you always pay for some resonator structure, is related to the Q factor of the resonator, right? So if I want to have a kind of a stronger coupling, I would use a higher Q, but that would limit my frequency range. It's like delta F over F, and that would limit what frequencies I can address. Now, if I'm not very greedy, and I know that I want to work at a magnetic field, which gives me this frequency, 2.8 gigahertz, let's say. Could I then use a resonator with a very high Q? No, because even if I tune my resonator to be kind of like optimal at the frequency that I want, I still want to change the field. I want to modulate, right? I want to do, let's say, a CPMG. If my resonator has a very high Q, I cannot change the field quickly, right? So I want to be, so when we try to build these structures or when we try to optimize them to our whatever application that we have to keep that in mind. That's, this is a general thing unrelated specifically to NVs. We use these resonators with a relatively low Q. It's somewhere between 10 and 100, which allows us to still do most of the, most of the manipulations and controls that we want to do. And for example, what we've done in this system is to demonstrate how we can do a high frequency sensing with it, which is related to what was done in Fedor's lab a few years ago with single NVs and now with this ensemble. But if we have this dense ensemble, then interesting things start to happen because if the NVs are very close to each other, they have dipolar interactions between them. And if they're close enough, the dipolar interactions are not negligible anymore. And if they're not negligible, then I don't know what happens. But it's interesting. So we wanted to try to see what happens in this many-body quantum spin system. How do you actually address that, or what do you try to do? You can try to play around with your Hamiltonian. You can try to control it or modify it so that you can measure whatever it is that you want to measure. The idea of controlling your Hamiltonian is well known from probably from NMR, like everything else. And it's called Hamiltonian engineering. The more modern word is Floquet engineering. By the way, this Floquet engineering, you know where this name comes from? What is Floquet engineering? Who was Floquet? Yes.
Don't know who was Floquet, but is it
Neither do I, it's
like
okay.
okay? So like Floquet means like if I want to give a like pi pulse, I don't give the pi pulse directly, but it's like the composition of like suppose 3 pulses, so that in the end it will effectively a pi pulse with the error in the pi pulses will like eliminate somehow in these 3 steps like this.
Yeah, so I think what you're trying to say, this is maybe one example, but Floquet engineering or Floquet whatever, generally is doing some periodic temporal modulation, some periodic change in your Hamiltonian. And then if you look at it in the period of your modulation, then you can get a new Hamiltonian with quasi-energy levels. You can diagonalize it, you can do whatever you want. And you have like these Floquet states, right? It's basically just going to a periodically modulated system. Now, Floquet was a French mathematician from the 18th century who came up with this nicely. And then a very nice physicist came up with the same idea 150 years later and got the Nobel Prize, but not in time, in space, right? If you modulate in time, this is what we just said. If you modulate in space, you get a Nobel Prize. Who was this? Where do you see spatial periodic modulations? Solid state. Who was it? Bloch, exactly. So Bloch waves, you all know. This is Floquet in space, right? So if you know Bloch waves, you know the idea of Floquet as well. And the idea of Hamiltonian engineering is to kind of go into that picture, go into that stroboscopic or periodic picture where you're applying some periodic modulation, and then stroboscopically after each cycle, you can look at the system and get an effective Hamiltonian, which is what you want. Okay, so you can induce this kind of effective picture by controlling the periodic modulation that you apply to the system. This is Hamiltonian engineering, and this is well known. My student Kevin was trying to do this for this interacting spin ensemble, and he was really annoyed. I wasn't, but he was. So he was looking at the two-body interaction Hamiltonian. You have terms that have, single spin terms, like the regular NV Hamiltonian, but you have terms that have interactions between spins. Now, interactions between spins, NVs, but, in general, are pretty involved, right? Because, they go in various directions, like this dipolar thing. So in principle, if you decompose the various two-spin operators, you can get like the simple scalar term. You also get vectorial couplings, but you also get like this tensorial, these tensorial terms. All of these appear in the two-body terms. So who cares? I definitely don't. So he just wanted to do, this Hamiltonian engineering. If you want to do Hamiltonian engineering, if you want to do some periodic modulation to change your Hamiltonian, you start building up all kinds of pulses, right? What kind of pulses would you try to build up? A bunch of pi pulses, right? That's what we always do. Why do we always use these pi pulses? Because it's super easy. right? It's very convenient, okay? So essentially, we always think about combinations of what's called the cubic symmetry group, which are a bunch of pi over 2 and pi pulses along x and y. And we build out of those all of the controls that we have, all of the dynamical decouplings and whatever. But why? Why do we use this? Why are we limited to these very specific building blocks? For example, you would imagine, I would imagine, I don't know about you, I would imagine that if I want to do some control, I will say I have the best AWG in the world, I have the best equipment. I will create any control sequence that will give me essentially what I want. I won't be limited to pi over 2 pulses or whatever. So why would actually you would like to limit yourself to these specific building blocks? Yes.
Because it makes our, you want to remain within the three-dimensional linear vector space, and these form a complete set.
Well, so that's mostly true. So even if I do this arbitrary control, then I'm still in the spin space, the original spin space. But what you're right about is the fact that in principle I'm covering all the various rotations or all the various controls that we can do, and I'm covering it in a continuous fashion, right? If I can apply any function, my basis is like this infinite continuous basis. On the other hand, if I limit myself to these pi over 2 pulses, I have a finite basis, and it's very easy to work with. I can optimize these very specific pulses that I apply, and then build out of them many different things. And that's much easier to do. And that works really well for many of us. For me, for sure. What Kevin realized, though, that when he tried to build out of those his Hamiltonian engineering sequence, is that they don't form a complete set. They're not enough. They do not mix all of these tensorial coupling terms because of symmetry. And he was not happy. So what he did was what all of you would do in this situation, would go to the next symmetry group, the higher symmetry group, and that's called icosahedral symmetry. The reason nobody uses it is because it's kind of annoying. You have to apply these Fermi, the golden ratio rotations around kind of weird axes, but it's still a finite set of pulses that you have to apply. And if you build out of this finite set the control, you see that you can mix everything. So if you can create these pulses, you can modify your two-body Hamiltonian to whatever you want, which you cannot do with the regular pi over 2 cubic symmetry pulses. Okay, and the advantage here, as opposed to doing just any random control, is that it's still a finite basis. And if it's a finite basis, I want to calculate what are the sequences that I need to apply to get a specific desired Hamiltonian. I don't have to, solve an inverse problem with continuous functions. It's linear algebra. It's called linear programming. Sorry, so this is what Kevin did. And he showed actually that he can build a sequence for decoupling all of the two-body interactions so that you can get the best magnetic sensor, the best sigma z term in your Hamiltonian. He did this for cubic symmetry, and he got this very nice sigma z term. The price he has to pay is a factor of 3 in the sensitivity, because you get a coefficient at the beginning. If you do the same thing with the icosahedral symmetry, you get a slightly more annoying sequence, but you win in sensitivity. It's a factor of 2 instead of a factor of 3. I have to say that even though this to me is very nice, people in NMR have already solved it in a different way, not with icosahedral pulses, and they can also reach this limit, but going beyond the cubic symmetry. They just add other pulses from outside of the symmetry group. It's called Dumbo, I think. But he wanted to create a quantum simulator out of this interacting spin ensemble, that realizes XY coupling Hamiltonian, an XY spin system. With the cubic pulses, you cannot do it. There's no way. You cannot mix the tensorial terms in a way that gives you just XY. With the icosahedral, you can. So this going up to this higher symmetry group is a nice extension of what people usually do. And it's quite useful when you're looking at an interacting ensemble because it allows you to do things efficiently that are difficult or impossible to do with the regular cubic pulses. And recently, what we've tried to do with Amir Abramovich in my group and a few others is to try to see what we can actually realize with these sequences. One thing that is kind of interesting to many people working with dense ensemble is to get the best coherence time that you can get, right? We talked a lot about dynamical decoupling. We want to increase our coherence time. That's usually good for sensing, but also for many other things. And if you apply CPMG, you know, the best dynamical decoupling sequence known to man, it's pretty bad. This is the red curve here. Why is it pretty bad? I remind you that CPMG is the best dynamical decoupling sequence known to man. So why is it not so good? What's different here than what I was talking about all along until now? Perfect, thank you. CPMG is the best for a single spin, for a single quantum system. When you have interactions, it does not do anything. So these interactions between the spins are sort of invisible to the CPMG, or CPMG is invisible to them, whatever. And they keep on mixing the spins despite this nice suppression of noise. So it doesn't really work as well. And we're not, of course, the only ones who've noticed this. And in Misha Lukin's group, they've worked on this, and they have very nice sequences that they've developed specifically to address these kind of interacting ensembles. They also have very nice names for them. This is like Droid R2D2 or something. The blue curve here, which is very nice. But they're still based on these cubic symmetry pulses, you know, this basis of pi over 2 pulses. And what we've been able to show is that we can do better with these icosahedral sequences by suppressing the interactions in a way that gives us a longer coherence time. And I think it's kind of interesting and still open to see how far this could be, you know, these types of control approaches can be pushed to utilize interacting dense ensembles for sensing, but maybe also, you know, to really study fundamental physics properties of these interacting spins, look at, you know, spin glasses and non-thermalizing states and things like that. So these are things that I think are definitely interesting.
What describes the decay curve now? What kind of functional form?
I don't know. So actually, it kind of seems like it's not a single. You know, if you think about it as kind of like exponentials or some type of time scale, it seems like there's more than one time scale in the picture. But to really tell you, you know, all of these approximate expressions that I showed before are not really relevant here anymore. And to really say what it is, I don't know. There are various approximations that can be done, but it's extremely non-trivial. And I think it's actually a very interesting question that we're trying to look at. Any other questions?
Why CPMG sequence doesn't work well for the interaction?
Yes, so it's a good question. And what I was trying to kind of explain earlier is the fact that, you know, CPMG is ideal for single spins because it really takes this single spin and decouples the interactions in the best way that we can, only limited by how good our pi pulses are, essentially. But it never knows about interactions between spins. So if you think about interacting spins, let's assume, for example, that our control is completely homogeneous. It does the exact same thing for all the spins. So we'll flip all the spins together when we do the CPMG pi pulses. but they can still flip between themselves. They can still interact between themselves, and CPMG does nothing about that. Okay? Under the assumption that the control is completely homogeneous, and that's what we're assuming here. So CPMG is optimal for single spins, but it does nothing for the interactions. So all the other curves that you see here are by adding kind of decoupling or suppressing also interactions between spins. This is called in NMR jargon, it's called homonuclear decoupling, because you're decoupling the interactions between same species spins. Okay? So sequences like that, maybe I'll say that in a bit, so I won't say that now, but that's the idea. By the way, this reminds me of a quick question. Some of you do sensing with NVs or with other systems, and you know that when you want to sense high frequency fields, not DC, not like I showed you before, but you want to measure like an AC field, you usually apply these sequences, these pulse sequences, but you don't usually use CPMG. You use something like XY4 or XY8 or something like that, pulses that are symmetrized in some way between the X and Y. But I just told you that CPMG is the best decoupling. So why not use that? Or the same question in a different way, why is CPMG the best? I will tell you. CPMG is really, really the best because what it does, if you remember when I explained it an hour ago, you do a pi over 2, you initialize your spin, and then you apply these pulses along the axis. So you're doing these small rotations, and you're least sensitive to any errors that you can have. That's the best sequence that you can apply. What am I assuming when I'm saying that I do this? I'm assuming that I know exactly where my spin is. Right? I rotated it here. In quantum information jargon, this is like doing nothing, because if you want to have a good memory with a long coherence time, the idea is that you don't know what the quantum state is. Maybe it's here. And then your CPMG is like the worst thing ever, right? So CPMG is the ideal thing when you really know what you have. But in most cases, when you want to have a quantum memory, or when you want to sense something, right? When I want to sense something, it's acquiring phase, it's rotating. So I don't want to kill that. I want to be sensitive to that. So for sensing anything, for doing anything sort of real, you want to have a sequence that's actually symmetrized and independent of the state that you're in. And that's why people invented XY blah blah. Okay? So you don't really want to use CPMG when you do any real sensing or do any real quantum memories. Okay? Any other questions about this before I move on? Cool. So, yes.
These are measured in ensembles, you said, right?
Dense ensemble.
How dense are the NVs, like in these samples that you mentioned?
A few ppm. I don't remember the number. 4, 5. Yeah, not something. It's not a super crazy sample, but it's one of the dense ones. Yeah. So it's a density in which the effective coupling between nearby NVs could be in the scale of tens of kilohertz or so. Other questions? Yes.
Is there any lower bound here? How far you can go with it?
What do you mean?
Means how long you can achieve T2 start, like dephasing time. Means here the green one is the best one, but is there any lower bound or theoretical lower bound? How far?
I don't know. I really don't know. So I mean, if I'm understanding and correcting and translating your question, you're saying, is this the best? The best? Can we do better? I don't know. So I'm definitely, well, not definitely, but I'm pretty sure that there's part of this relaxation here also includes imperfections in our control. one of the advantages of this sequence compared to the droid, for example, is that we can realize it with a smaller number of pulses, so we're less sensitive to pulse imperfections, but maybe there's something better. So this is not provably the best, but I don't know. It's an interesting question. Yes?
I have a silly doubt. So you are applying pi pulse at different directions, right? So if you look into the hardware setup, how are you literally like giving the pulse at different directions?
Great question. And actually, I wanted to ask you this. So if you remember, well, most of you know, pi over 2, pi pulses, we apply these things using our regular microwave equipment. And when I try to apply these icosahedral sequences, I want to apply pulses of area 2 pi over 5 or something like that at angles away from the XY plane that are like at the golden ratio or something like that. So it's a kind of a strange axis to work with. How do you realize that experimentally? How would you be able to, for example, create a pulse that's not in the XY plane? And thank you for the question, but I will not answer it because I leave it as exercise. That's so annoying, sorry? I'm sorry, I cannot hear you.
Can you polarize the microwave, but can you polarize it, change the angle somehow?
Bless you. Polarizing the microwaves will probably not help you to tilt. It could help you just in principle to do this technically better. In our experiment, we don't polarize the microwaves. But I think polarizing them would be useful, but would not solve the problem completely. Anyway, you can ask me later if, yeah.
Question regarding your previous slide when you show these representations, or maybe with slide is here. So you have reduced presentations with G1 and H, right? But is it for, does this thing works only for NV? I mean,
for any dipolarly coupled, it's basically just magnetic dipoles coupled with dipolar interaction. That's it.
General.
Pretty general, yeah.
Okay.
Yeah. Any other questions? Okay, so I wanted to mention that, there's this, people asked also, but I also was discussing spin bands or some noise that you have around you. And maybe one can think about using the NV to do something called hyperpolarization. This is, again, a term from NMR. In atomic physics, this will just be called polarization, but hyper sounds better. And the idea is to try to, the NV is fun. We shine green light, it's initialized to 0. In NMR jargon, this is hyperpolarization. We've polarized it. Why is it called hyper? Because it's as if the spin is at a temperature that's lower than the actual temperature of the system. So if I polarize this, at 100%, just by shining green light, the effective spin temperature is 0, right? So I'm sort of, this is the world's smallest refrigerator. I'm cooling down the NV, the spin temperature of the NV. Now, can I use this NV as a resource to cool down the spins around it? Why not? And if I can cool them down, then maybe they will not create as much noise. They will not decohere my NV as much, for example. Or maybe if I cool them down, I can use them as a resource for something. And one of the ideas that came out of this was part of this European project was to actually cool down a sample of interest. So hyperpolarization is definitely not our invention. It's been around for many, many years. And when you do MRI, for example, the MRI system is measuring spins in your body, right? Water. But you need a huge magnet. Why do you need a huge magnet? Because the spins in your body usually are about room temperature, a little bit higher, and they're mixed. So you want to get a bigger signal, you want to polarize them. How do you polarize them? You put in a large magnet. The large magnet fights thermal noise, right? If you could instead, and let's say this is a scenario where you don't want to measure necessarily the water in your body, because that would be hard to do, but you want to inject, people do this, medical scenarios where you do this, you inject some contrast agent into the patient, and you want to measure that contrast agent in an MRI machine, for example. But let's say instead of injecting just, this contrast agent, I could before then hyperpolarize it, right? I can cool it down, hyperpolarize it, and then inject it into the person. And if I do that, the signal out of this contrast agent, all the spins will be aligned. So I will get a better signal. This is kind of an idea that's been around for a long time. And what is the common way of doing this hyperpolarization? What would you do based on what I just told you? Perfect, thank you. And in addition to the strong magnet, you cool everything down. So people, I mean, I don't think this has ever gone into real clinical use, but there are many machines like this. You have like a cryogenic system with a huge magnet, you put in the contrast agent, low temperature, high field, it polarizes, and then you take it out. If the spin relaxation time of the relevant nuclear spins is slow enough, you can take it from one room to the other room, inject it into the person and measure. This is highly inefficient, highly expensive, doesn't really work well with real world scenarios. So what we were thinking is we can use the NV as a source of polarization. I won't go into the details of the project. It worked, but not well enough, because it has to be really, really efficient, right? You really have to polarize a huge amount so that you can actually see this. So it's very hard to do. There are other tricks that actually work better. But I want to tell you about the physics, the basic idea of this polarization scheme. How does it work? Here, it's not like the dense ensemble of NVs where they're interacting with each other and they're all the same. Now we have NVs and some other spins. In this example, the other spins are nitrogen spins, for example, but they could be anything, right? But usually, when these are two different spins, they have different resonances. If I want to use the NV, you see the NV is cold. I applied, a green pulse, and it's all polarized to the ground state. But the other spins are completely mixed. They're at room temperature. I want to cool them down, so I want to flip-flop them. But the energies are different. So how would I do it? Thank you. Like the heart. So how do I do it? I could scan the magnetic field, the biased magnetic field, in such a way that would bring these two into resonance. Or I can do something that's, you remember Hahn, the magician from the Hahn Echo? So there's a Hartmann-Hahn scheme which basically says, let's go into a rotating frame where I drive these spins and bring them into resonance there. And the idea is that if I drive each one of these spins in resonance, I can in the rotating frame, I can make these frequencies equal, and then a flip-flop process can occur efficiently. This works really well in PowerPoint, but in reality, it's not that easy. But in principle, this idea can work, and there are nice examples of doing this, driving a resonance to transfer polarization fast in this Hartmann-Hahn resonance, and also this was done in Fedor's group with this magnetic field tuning, and here it was polarizing C13s. And you can actually see not only do the C13s get polarized, the coherence time, or the T2 star time of the NV, improves. It becomes longer when you polarize these nuclear spins because you're suppressing the noise, you're polarizing them. So this is a pretty nice demonstration. A lot of time passed since these experiments, and people have already realized, actually it's the next slide, but people have already realized how to do this better. So in Fedor's and Martin Plenio's groups, they've developed schemes that do this very efficiently, and they use it. But if we want to polarize, like in this MRI example that I gave you, we want to polarize a lot of spins. We really want to cool down kind of a significant amount. So we wouldn't want to use like a single NV. We would like to use a huge ensemble, right? But if we have this huge ensemble, and like I was telling you before, the spins are interacting with each other, that kind of interferes with the polarization, the hyperpolarization process, right, with the cooling. So we want to take this into account. So we want to somehow suppress interactions This is, by the way, one of the standard homonuclear decoupling sequences from NMR. It's called WAHUVA. There are others. So we want to suppress these interactions to get better hyperpolarization. And this is the sequence that we've come up with that's based on these icosahedral pulses that allows us to do this decoupling. And we started to work with Martin from Martin Planio's group. And the sequence that they've developed is called pulse-pol. Was demonstrated several times. It works really well. These are simulations. The experiment has not been done yet, and I apologize for that. But what you can see, I know I should. Well, what you can see in these simulations is that pulse-pol works really well. The x-axis here is time, and the y-axis here is the polarization, where the yellow is the NV, or the electronic spin, and then the blue is the target spin, like the nuclear spin. And you can see that polarization is being transferred from the NV to the nuclear spin and back in a very efficient way. This is the standard pulse-pol. These are simulations without any interaction. So it's like a single spin coupled with a single spin, right? No interaction. So we can combine this original pulse-pol sequence with our decoupling sequences that we've developed from these icosahedral sequences, and we see that we can still get very nice polarization transfer, not as good as the original pulse-pol, but okay, using this combined sequence. However, if you introduce dipolar interactions between the NVs into this simulation, then you can see that the original pulse-pol doesn't work. It's like CPMG, it's good for dynamical decoupling of single spins, but when you have many, it's pretty crappy. Polarization is not being transferred anymore because it keeps getting flip-flopped within the NV, interacting NV system. However, with this decoupling sequence, it's nearly the same as without interaction. Of course, it's a simulation, so this is not surprising, but it works really well, and we're now trying to do these experiments to see if it actually works. Okay, so with the time that I have, let me tell you a little bit. Any questions about this? Yes.
How you know there exists interaction between NV centers?
Well, so it depends on in which scenario, but in the dense ensembles, we see it. So we just see that things don't work as we expect them to work for single NVs or for samples with lower densities. So there actually we had some bless you. We had some ideas on how to really quantify the strength of the interaction of NVs. We actually developed sequences that distinguish between just relaxation because of noise versus effects of coupling between NVs, and there are various ways to do this. But usually when you try to do your regular experiments, you see something that's behaving weirdly. If you've, I think Arnie noticed this, but if you look at the relaxation, it doesn't look like what you'd expect. It has several timescales. We see these things popping up in very dense ensemble.
Generally, about what density of NV centers?
Again, this is a question that is related to the specifics of the sample that you have, what are the coherence times, and so on. In general, I would say that this starts to be noticeable in standard experiments starting from a few ppm, but again, it depends a lot on specific parameters. Other questions? Okay, so with the time I have left, I'll tell you a little bit about sensing. And we've sort of touched upon this a little bit before, but essentially when you have this optical access and you have these magnetic sensing schemes, the simplest being this ODMR that I mentioned before, we can incorporate this into kind of microscopy, optical microscopy setups to do magnetic imaging. And these are, and now maybe the question becomes, why would you do it? Why is it good? What is it good for? And apparently, this type of magnetic sensing or magnetic imaging can be useful when you're looking at relatively small samples and when you want to get quantitative measurements of the quantitative vectorial measurements of your samples of the magnetic field. And this is something that NVs do really well. So these are examples of measurements that we've done on magnetic van der Waals materials. Specifically, this is iron germanium telluride that is exfoliatable, so we can actually take flakes and put them on top of the diamond. And the people who've done it actually been to it. Amandeep are sitting here. These are images of the color bar is tray magnetic field. These are images of the magnetic structure and domains that we can see in such flakes. And the different images are taken at different temperatures. So we can actually scan the temperature. Luckily, maybe not luckily, we chose it this way. This material has a TC that's close to room temperature, so we don't have to go to cryogenics or anything. And we can really change the temperature and see the magnetic phase transition. And more so, we can even see how the domain structure changes with temperature. In this specific example, we found some weird crystallographic effects that we were not expecting. But it's a useful tool for studying these types of magnetic materials as a function of parameters such as temperature, external field, and so on. Another thing that one can try to do, and I know from some of the posters that some of you are also doing this, is to try to see if you can measure noise. And by noise, I mean not necessarily do this noise spectroscopy that I mentioned before, but just something that's called relaxometry. Try to see if you can measure, some sample that you're interested in that creates magnetic noise the NV feels. One such type of sample would be radicals, which have unpaired spins, unpaired electrons, and therefore they could create magnetic noise, which your NV would feel. How would your NV feel this magnetic noise? Let's say you have your NV system. I don't know, in this case, we wanted to do imaging, so you have a dense layer of NVs close to the surface. It has, its own properties. I can take it and measure, what are the T1, T2, whatever properties of the system. And now I want to measure the sample, these radicals that I put on top. What would they do to the NVs? How would I measure? What would be the signal?
So NV has its coherence time, but if we put a lot of things that fluctuate on top of it, it would be really hard for it to stay coherent as long as it could. So
exactly. So
the reductions you want.
Exactly. So you would expect this to manifest itself as some additional noise on your T1 coherence properties, whether it's T1, T2, whatever. What would be most sensitive to it depends on the correlation time of the noise. If the noise is slow, you would probably see this effect more on T2 or T2 star. If the noise is fast, you might see it on T1. So people do a lot of, specifically for radicals, they're very fast, they fluctuate quickly. So people usually do T1 relaxometry. And we wanted to try to do this. This was done in collaboration with Uri Banin from our chemistry department. We're trying to do this to characterize radical concentrations. And like everybody, we try to do relaxometry. But this is actually a relaxometry measurement. We want to see how T1 changes with the concentration. But this was done not with radicals, but with gadolinium. When we tried to do this with the radicals, we saw that the effect was really small. We couldn't really measure anything. However, without planning on it, my student, Yoav, looked at the fluorescence properties of the NVs, and he saw that he gets less fluorescence when the radicals are there. And when he was a little bit more careful, he noticed that if you remember, the NV minus always has his friend, the NV0, there could be charge transitions. There could be ionization recombination processes happening. And these radicals, they're not only an unpaired spin, they're an unpaired electron. They change the electric field environment of the NV, and they can cause ionization of the NV minus into NV0. And this is actually what we've seen. So we've noticed that we can measure the concentration of these radicals through the charge state of the NV rather than the spin relaxation. And in this experiment, we were looking at radicals created in, where is that? Never mind. Created in hydrogen peroxide, so we can use a blue laser to create radicals in the solution. And that's a really nice experimental knob. So the stronger the blue laser, the more steady state concentration of radicals we have. So in this experiment, for example, we're measuring the fluorescence out of our system, and then we have these different curves, red and blue for NV minus fluorescence, and actually, I don't know, these are different reds. Maybe this is yellow, I don't know. So this other red and black for NV0, and the difference between these two colors are, a bare diamond without any solution on top, and the diamond covered with the solution. In both cases, we turn the blue laser for this period and then turn it off. And you can see that as you turn on the blue laser, you're creating radicals in your solution. The fluorescence of NV minus is reduced. The fluorescence of NV0 grows. And we actually measure this just by looking at filtering out fluorescence out of fluorescence coming from the different charge states. And one can actually quantify this and measure the change in fluorescence both for NV minus and NV0, and then the normalized difference as a function of, this is blue laser power. So this is the actual power of the blue laser we apply. But one can calibrate this axis to radical concentration, which is something that we've done separately, on large amounts in a different system. So one can really get a linear dependence of the power with the radical concentration, allows us to get a sensitivity to these radicals using this system. So this is kind of an example of how you can use NVs to sense various things, not necessarily magnetic fields or magnetic noise. In this case, the electric noise from radicals. And this could be somehow useful and complementary to standard relaxometry techniques or to in other scenarios. And it eventually gives you a relatively good sensitivity with being quite simple. So it doesn't require any microwaves or anything, and could be quite non-invasive. Sorry. I wanted to mention briefly that there are standard magnetic sensing techniques that we've been discussing. The regular ODMR that I showed you before is a little bit silly when you think about it, right? I want to measure, when I want to measure the magnetic field, in this kind of magnetic imaging that I showed you before, I essentially want to identify the resonances of these dips, right? If I know that this x-axis is the frequency, this is the fluorescence that I measure. If I know at what frequencies these dips occur, I know what the magnetic field my NVs feel, right? Why are there 8 dips here? This is just because this is an ensemble, and we have all the 4 different orientations, crystal orientations of NVs. So we get a pair of dips for each orientation. So how would you do this in an experiment? You scan your frequency, your microwave frequency, measure the fluorescence, and then once you've measured this plot, you can fit it and find the resonance. But it takes a long time. It's pretty slow. You have to really take images for each frequency. So John Howell was very upset, and he said, I know compressed sensing. So he said, let's do compressed sensing for this. The idea behind compressed sensing is completely general, unrelated to NV specifically, is to say, if I want to measure something that is sparse in some basis, then I can do this in a smart way. I can choose the points to measure and in a kind of a random distribution, where each measurement then, each measurement point is then chosen by some overlap between what I measured so far and what I'll measure next. So what this process actually does, in our case, the signal that we're measuring is extremely sparse in this Lorentzian function basis. We can use this basis, and sorry, I don't know if I can do this in here. Let's see if this works. So when we do this experiment, we actually try to find the Lorentzian functions that span the measurements the best that we can. 1 minute? No. 3. Okay. Thank you. So we try to find the best measurements that fit. And actually, just the bottom line to show you is that we can get, this is the error in our measurement as a function of number of measurement points, comparing compressed sensing to this regular scanning. And you can see that the compressed sensing works better at lower numbers of measurements. So you do pay some price in terms of your error, but you can get a much lower error for fast measurements. So you can find sometimes a better compromise between bandwidth, how fast you measure, and your sensitivity. Once we did this experiment, our friends Filippo and Stefano said, machine learning can do better. And these days, everybody knows that machine learning can do better in everything. And unfortunately, it's also true here. So, so they've trained a network on a combination of experimental data and simulated data, and then tested it on our measurement data. And what they've showed is kind of similar to compressed sensing, but even better. So the error that you get is not as good as the best scanning that you can do. But if you go to very rough scanning, not taking very precise frequency points, the regular approach really sucks. But this machine learning thing is, is unbelievable. You can take like 20 points and really get a decent fit. I'm not sure why, to be honest. But somehow it works well, and we've uploaded these things. So what you do need to do is you need to take this network and train it for the specific diamond sample that you have, so that it's trained on, what these ODMRs look like in terms of contrast and width, usually, and then it works relatively well. So I'm out of time. I want to thank you for your attention. I hope I sort of told you a little bit about why color centers and NVs specifically are really cool. I want to thank all the students and people who have actually done the work, our collaborators and funding, and I want to thank you for your attention. Thanks a lot.